Okay, this lesson is exponential functions, which is taken mostly from sections 7.1 and 7.2. I'm doing this not in front of the class, so if I go fast, pause, right? If it's too fast, pause, especially when you get to the U-tries. Exponential functions are a new kind of function for us. They are to be understood in combination with logarithmic functions, which we get to next class. Today we will definitely look at the graphs of exponential functions, and we will be introduced to the concept of asymptotes. And these other bullets we'll get to next class. Exponential function is a function which has the variable in the exponent. The standard format is y equals a times b to the x, right? The b is the base. A and b are real numbers. Now a cannot be 0, or else it would be y equals 0. B cannot equal 1, or else 1 to the x is just 1 all the time. And b is definitely supposed to be greater than 0. There's two kinds of exponential functions that we learn about. One is growth and one is decay. If b is greater than 1, meaning the base is greater than 1, what's being raised to the power, that's growth. If b is less than 1 but greater than 0, then that's decay. And students have encountered some of these in their other classes, like exponential decay is half-lives that they study in chemistry. Exponential growth can be population models in biology. And we're going to talk about another exponential growth application, which is compound interest. So before we know anything about the graph of a function, we plot points and just see what we think it looks like. So in this case, I'm going to graph a simple exponential growth. It's growth because that number is bigger than 1, right? And it looks like if there was if I'm comparing it to the y equals a times b to the x, that the a is 1. That's why we don't see a number multiplying times 2. Right? I already put in the x values of -3 to 3. So now let me use those to create a table of values. Right? If I plug in -3 for x, then y equals 2 to the -3, which is 1 over 2 to the +3, which is 1/8. 1/8. Right? If I do 2 to the -2, I'm going to get 1/4. 2 to the -1 will be 1/2. 2 to the 0, anything to the 0 is 1. 2 to the 1, 2 squared, and 2 to the 3rd. Okay, those are our points that we can graph now. -3 1/8 puts it right above the x-axis. -2 1/4 is a little higher. -1 1/2 is a little more. 0 1, 1 2, 2 4, and 4 3 8. So we make a table of values, we plot some points, and we hope that it kind of gives us some information about what the shape of this function graph is, and it does. It looks like it goes like that. And it's, again, this is the exponential growth model, because the graph is increasing from left to right, right? Over the entire domain, it looks like it's increasing. Now, exponential, if somebody says something grows exponentially, what they mean is it grows really quickly. Even if it doesn't grow technically exponentially, people use that expression all the time. Now, one thing that we have to look at a little closer is what's going on the left side of this graph. I mean, it was at 1/8 at -3. What if I put in x equals -4? That would be 1/16. Then it would be 1/32 and then 1/64. In every case, it's going to have 1 divided by an increasingly big number. So this value is going to get smaller and smaller and smaller. But will it ever equal 0? And the answer is no. It'll be a very small positive number, but there's no way we can make this function equal 0. Okay. When a graph approaches some line on the graph infinitely close, but it never touches that line, that's actually a new concept for us. That is called an asymptote. And usually we will draw that onto the graph. Dashed line. I did it in red just because I can. But what it says is that the graph is approaching that line, but it's never going to touch that line. Okay, so again, this line is called asymptote. Okay, because it's a horizontal line, it is a horizontal asymptote. And the equation for that line, in this case, is y equals 0. Okay, the domain of this, the domain of all exponential functions is all real numbers. So we don't need to answer that question again in this lesson. The domain is always all real numbers, which means you can plug in anything for x. There's no values of x that are restricted from the domain. The range is not all real numbers. Right? You can see that this graph doesn't go infinitely up and down. It's only above the x-axis. In fact, it does not even touch the x-axis. So to describe the y values, the y coordinates of all the points on there, we're going to say y is greater than 0. Right? Does never equal 0 because the graph never touches the x-axis. Right? The parent function for an exponential growth is f of x equals b to the x. Right? Doesn't even have the a multiplying. It's just a base greater than 1 raised to the x power, which is pretty much what we just looked at. We looked at 2 to the x. In general, b to the x is the parent function, and the graph looks like this, right? It has an asymptote. It has an asymptote on the x-axis, which means it approaches it becomes infinitely close to it without touching. It has a y-intercept of 1, right? Because it's not being multiplied by anything. It has the point 1b. That just means if you plug in x equals 1, then y equals b. And it basically is increasing very quickly into the first quadrant. The domain is all real numbers. The range is y greater than 0. Okay, we can say that it's always increasing from left to right. We can say that as x approaches infinity to the right, that y is approaching, you could see that this graph is going infinitely up, so y is approaching also positive infinity. Okay, that's not what's going on the left. As we go to the left side of the graph, which means x approaches negative infinity, the graph is actually, approaching the x-axis without touching it. So we would say that y is approaching 0. Right, so end behavior can be that the graph veers off towards infinity or negative infinity, or it could be that it approaches a horizontal asymptote. Now, just to show the effect of b, b is part of the equation for the parent function. It doesn't much matter to us what the b is, right? I've got 2 to the x and 3 to the x on this graph, which I copied from the calculator. And you can see that, of course, 3 to the x will increase faster than 2 to the x. But all the rest of the particulars are the same. There's still an asymptote on the x-axis. There's still a y-intercept of 1. The domain is still all real numbers. The range is y greater than 0. So all the things that we really look at are not changed by changing the base from a 2 to a 3 or to any number greater than 1. Okay, so don't look at the change of the b like it's a transformation of the graph, because it's not. Which brings us to transformations, right? Transformations of exponential functions work the same as they worked for absolute value functions, right? The a determines up or down. Stretch or shrink. The h determines horizontal, shift. Right? We know that minus h will mean right, plus h will mean left. The k is a vertical shift. Right? Plus means up, minus means down. And that is exactly what will happen with all of those in the exponential. So we have to remember the basic shape of the exponential graph and then move it around like we moved around the absolute value function. So what is the effect of a multiplying by a number less than 1? And the answer is that should shrink the graph. Meaning it will go, the y values will increase more slowly. What is the effect of a minus in front of a graph? The answer is a flip across the x-axis, or as we say, a reflection in the x-axis. And there's the graphs. So notice that this 1/2, again, it's a shrink. And what has it done? It's changed our y-intercept. Our y-intercept used to be 1, and now it's 1/2, which makes sense, right? And when x is 0, 4 to the 0 is 1, and now 1 times a half is a half. Okay, but the shape of the graph is basically the same. The domain and the range, unchanged. Okay, when we flip the second graph, so now it's going down, it's still exponential growth, it's just growing in a negative direction. The y-intercept of 1 becomes a y-intercept of -1. And besides that, it's essentially what we expect from an exponential growth. The domain is still all real numbers, but the range is not what it was before. Right? Because now the graph is below the x-axis. We have to say that the range is y is less than 0. Okay, what's all going on in this one? We have a stretch. We have a right one. And we have a down 3. Now what's interesting to us here is that one of those is going to move the asymptote. And remember, so Think of it, we have a horizontal asymptote on the x-axis. If I move that horizontal line left or right, it doesn't change the position of the line. But if I go down 3, that is definitely going to change the horizontal asymptote. If the whole graph moves down, then so does the asymptote. So let me draw in our new asymptote, which should be at y equals -3. And I'm going to put it on there, and I'm going to label it. Okay, and now just to have a couple points to graph, I know what the basic shape is, but I know it's been stretched and shifted. I'm going to plug in a couple values for x. And how about I use 1 and 2? Yeah, 1 and 2 is fine. Right, if I put in x equals 1, now I've got 2 to the 0, which is 1. 4 times 1 minus 3, which is 1. If I put in x equals 2, I'm going to get 2 minus 1, so it's 2 to the first times 4, which is 8, minus 3 is 5. Okay, if I graph those 2 points, I've got 1, 1, and I've got 2, 5. I could actually do one more, since it's still going to cross the y-axis. If I put in a 0, I'm going to get 2 to the -1, which is 1/2. 1/2 times 4 is 2, minus 3 is -1. And that's plenty enough for us to see this graph. Kind of a wiggly line. Okay, what is the new range? Again, this graph is above the line y equals -3, so the range is y greater than -3. So these are going to be the U-tries, and if you want to follow along, then you might want to hit pause now, and I'm going to go ahead and do them. When you're done, hit play. So y equals 4 to the x is actually just another parent function. It has no transformations going on at all. It still has a asymptote on the x-axis. Close enough. It still has a y-intercept of 4 to the 0, which is 1. It still has, I can put in 4 to the 1 and get 4. So here's the shape of the graph. Right, the domain is all real numbers, and note that when you look at a graph like that, or you see that line going up so fast, you may have a hard time believing that it actually goes to the right, but it does go to the right. Right, you keep putting in x values, you're getting y values. They're going to be so far up here you're never going to see them, but they're there. So the domain is unchanged. The range is actually unchanged. This is the parent function. Range y greater than 0. Okay, here's another one. Go ahead and hit pause if you want to try this without me. When you're done, hit play. Okay, we have a shrink. But other than that, no transformations. So our asymptote is still in the same spot. I can make a little table of values here. At x equals 0, I'm going to get 3 to the 0 is 1 times 1/2 is 1/2. So the new y-intercept is 1/2. And when I put in x equals 1, I get 1/2 times 3, which is 3/2. And that is plenty to see this graph. And the domain and the range are unchanged, right? Domain all real numbers, range y greater than 0. Okay, here's another you try. Hit pause if you're going to do it by yourself. Hit play when you're done. Right, this one has a left 1 and an up 2. And we know that the plus 2 is the one that's going to shift the asymptote. It shifts the whole graph up 2. That will definitely move a horizontal line. So I need to move that line first. The new asymptote is the new asymptote is at y equals 2. If I do a little table of values to give me some points, how about if I use -1 and 0? When x is -1, then it's 3 to the 0, which is 1 plus 2, 3. When x is 0, it's 3 to the first, which is 3 plus 2 is 5. -1, 3, 0, 5. Sketch the graph. Okay, the domain is still all real numbers. The range y greater than 2. Okay, compound interest is one example of a exponential growth function that's used in real life, right? And it'll be useful to you some point in your life, no question about it. Compound interest is how we earn interest. If you have a bank account which gives you an annual interest rate, they probably compound that interest monthly, which means they don't give you your annual interest rate once a year. They give you 1/12 of your annual interest rate once a month. But that works to your advantage because after the first month, you've earned a little interest that adds to your account. And now when the next month you get your 1/12 of the annual interest rate, it's not only calculated based on what you put in at the beginning. It's actually got that little extra that was put in after the first month. And in the third month, it's got that little extra that was put in the first 2 months. In the fourth month, etc., etc., etc. I mean, compound interest can be a very powerful thing. I mean, there's a famous quote attributed to Einstein, something along the lines that compound interest is the greatest power in the world, or something like that, which he probably didn't say, and if he said it, he probably didn't mean it, because I think he knew about real powers like nuclear bombs and things like that. But it's still, what the point is, compound interest is important. And you could see its exponential growth when we consider what all these letters represent, right? The A is your amount of money. The P is the principal. How much should you put in at the beginning? The R is an annual interest rate in decimal form. And N is how many times per year it's compounded. So monthly is 12. Daily would be 365. The thing about R and N, they're both positive. And since 1 plus R over N is the base of this thing, that is definitely going to be a number bigger than 1. So this is exponential growth. So that's greater than 1. T is the number of years that your money is sitting wherever. And I'm doing this only in terms of money, but I guess it probably has other aspects to it. So one is, we're not going to do any work with this. I think if you get to math analysis next year, you will, because you go a little deeper into exponential and logarithmic functions. But the thing that we need I wanted to point out is that the more times you compound, the more money, the more the amount of money, A, that you have. But it's not, there's got to be a limit. I mean, if I go once a day, that's n equals 365. What if I go once an hour? You know, that's 365 times 24 hours in a day. What if I go once a minute, right? That's 365 times 24 times 60. I mean, there's got to be a limit. And in fact, there is a limit, right? And if we, in this formula here, if we let the n grow infinitely, n approaches infinity, then actually our formula changes. And you can see the new formula. It's still got the A and the P and the R and the T. But now it's got this new letter, E. And E is an irrational number, kind of like pi. It has a value 2.7182 dot dot dot. You know, it's never going to terminate. It's never going to repeat itself, just like pi. But it's definitely a number bigger than 1, which makes this exponential growth. And when we get to the next lesson, we're going to find out that E is actually the base of a special logarithm called the natural logarithm. And when I've Googled this in the past, like I just wanted to see, you know, what would be the common explanation for what E is. What I found is that it says that E is the base of the natural logarithm. Okay, but as you see here, we're using E. It has nothing to do with logarithms, right? It's in the exponential mode only. Okay, now we're looking at exponential decay. And remember, decay means that the base is less than 1. It's greater than 0, but less than 1. So this is going to be a decay. And we're just trying to scope out the general shape of an exponential decay graph by plotting some points and connecting them with a line. So 1/2 to the 0 is 1, 1/2 to the first is 1/2, 1/2 squared is 1/4, 1/2 to the third would be 1/2 times 1/2 times 1/2 is 1/8. Okay, 1/2 to the -1 is like 2 to the +1. 1/2 to the -2 is like 2 to the +2. And 1/2 to the -3 is like 2 to the +3. So these numbers should be familiar. They're the same numbers that we used in our table of values for exponential growth. They're just reverse their order. So let me graph these. -3, 8. -2, 4. -1, 2. 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. So the graph is similar shape. It still has an asymptote on the x-axis for the same reasons it did before. Right? It still has a domain of all real numbers because all exponentials have a domain of all real numbers. And it still has a range of y greater than 0. Okay, now it's decreasing though. So the parent function for exponential decay is pretty much the same as the parent function for exponential growth, just that the b now is between 0 and 1. And like we said, all the other particulars are the same as exponential growth. So I'm not going to stay on this slide long. If you want to copy it, then pause. Now one thing to keep in mind is, if you want to say y is 1/2 to the x, that's actually the same thing as saying 2 to the negative x. And we can see why that is, because when you have a negative exponent, and when you have a negative exponent, the way you get rid of that negative exponent is you flip it. And there you go. It's the same thing. So sometimes we define exponential decay as having a base less than 1. Sometimes we define it as having an exponent, which is negative. Now remember, when we talked about transformations on the very first day, we talked about, obviously, if you want to flip the graph across the x-axis, you put a negative in front of it. If you want to flip the graph across the y-axis, you actually put a negative in front of the x. So notice the difference between 2 to the x and 2 to the negative x, and now look at their graphs. So in fact, we can look at exponential decay as a transformation of the graph of exponential growth, right? It's a reflection in the y-axis. And there's the graphs that go with it. Okay, now we're going to do the same thing that we did with the exponential growth. We're just going to look at a few graphs and transforming a few graphs. There we've got a stretch. Here we have a, I'm just going to say flip and stretch. So the graphs look like that. Right, so this is, notice, before we multiplied by 2, it had a y-intercept of 1. Multiplying by 2 stretches the graph, which turns the y-intercept from 1 to 2. Okay, now you can graph a couple other points just to give it a little bit of a shape, but we understand what it looks like there. And this one too, it's been flipped and it's been stretched. So the y-intercept was 1, then it was flipped to -1, then it was stretched to -3. So the graph on the left has the same domain and range. The graph on the right would have a range of y less than 0. Okay, a little bit more going on in this one. Right, we've got the stretch. We've got left. And we've got down. So I'm always, first step, going to draw in my asymptote. The asymptote should be y equals -2. I'm going to make a little table of values just to get a couple points. All right, since it's an x plus 1, how about if I use -1 and 0? All right, if x is -1, then it's 1/2 to the 0, which is 1. So it's 3 minus 2, which is 1. If x is 0, then it's 1/2 to the 1. So 1/2 times 3 is 3/2. 3/2 minus 2 is -1/2. So graph those 2 points, -1, 1, 0, -1/2. And understanding the shape of this graph, we can sketch in something. Right. The domain is still all real numbers. The range now is y greater than -2. So here's your U try. I'll go ahead and hit pause if you're going to do it, and hit play when you're ready. It's got a stretch and a flip. I say flip, and then I put X to say flip across the x-axis, and stretch. And that's about it. So it's not shifting the asymptote in particular. So let me sketch that in. Let me graph a couple points. Well, first let me draw that. Y equals 0. Make a table of values to give me a couple points. How about we use 0 and 1, right? If I put in x equals 0, I get negative 2. If I put in x equals 1, I get 3/4 times negative 2, which is negative 3/2. 0, negative 2 is here. And 0, 1, negative 3/2 is here. And then I sketch the graph. Now the domain is all real numbers. The range is y is less than 0. Last one. You try. So hit pause, hit play when you're ready. Right? We got to right and up. Draw my asymptote. If it's up 1, that means the asymptote now is at y equals 1. Right, I'm going to plot a couple points. If I put in, let's say I put in 1 and 2. Right, if I put in 1, I'm going to get 1/4 to the 0, which is 1, plus 1 is 2. If I put in 2, I get 1/4 to the 1, plus 1 is 5/4. 1 and 1/4. So I plot those 2 points. 1, 2, 2, 5/4. And I could do the 0 just to have it, since it's there. 1/4 to the negative 1 is 4. 4 plus 1 is 5. So here's our graph. And domain all real numbers, range y greater than 1. And that does it. So exponential functions. Next class we're going to talk about logarithms, and that will address the parts of these 3 essential learnings that we haven't got to already. Okay. And that is the homework.